everybody. Today we're going to work on two new concepts. One has to do with energy, and we're going to do so. We're going to look at energy by way of a graph, and the other one is going to be another E word called enthalpy. So I want to start on energy, and the best way to do that is by way of these two graphs that you see. We have an example of an exothermic graph here on the left, and we have an endothermic graph here on the right. Now, what is the difference between something that's exothermic and something that's endothermic? Well, in exothermic reaction, heat exits. That means it's given off by your reaction. In an endothermic reaction, heat enters. And what it enters is the system that's being studied, whatever those chemicals might be. So let's focus on the exothermic graph first, and we'll try to make some sense of all this stuff we see, and then we'll move on to the endothermic graph. Okay, so on the y-axis you can see potential energy, and on the x-axis we see reaction progress, which you can think of like time. So at the beginning of the reaction would be over here on the left, and as you progress through it at a later time would be over here on the right. And you also see an initial reactant energy level. And you can see this horizontal line here represents the current energy at which your reactants are at. Now, what are your reactants? Well, they can be anything. They can be two chemicals that you decide to mix together. So let's say you have one chemical in one hand, you have another chemical in the other hand, and you decided to combine the two chemicals into one large beaker and see what happens. The chemicals are reactive, so what's going to happen upon initially putting them together, and maybe you give it a little stir, is those chemicals will start coming in contact with one another. And that's what's going to happen in this part of the graph right here. After the two chemicals start finding one another, the atoms that make up those chemicals start mingling with each other, and they are going to basically start forming some pseudo bonds, some new bonds that are about to form. So we're right at the point where it's a little bit shaky. We're forming these what's called activated complexes, which will be right here at the top, activated complex. And after the two chemicals, their constituent atoms, the atoms that make them up, find new partners. The partners will then bond to each other, and what's going to happen is you see this major drop-off here in potential energy. Reason why we see the drop-off is because those new partners that the atoms bond with are a better fit for those atoms than their previous partners. How do we know that? Because we look at the product energy level, which is way down here. So the potential energy has dropped really low, and that means increased stability. That means that the partners that were found were much more stable than the original partners, which had a higher potential energy. So up here is where all the getting together with the new partners happened. The complexes of new chemicals got activated, and as they started bonding together, the potential energy kind of fell off a table, and we see that the curve goes almost straight downward by the end. Now, there is a difference between the reactant energy level and the product energy level, and that energy released has a symbol. It's called delta H, and it represents this word, this second E word, called enthalpy. We'll have more on that in just a minute. Enthalpy. Okay, one additional thing that I wanted to mention here was the idea of a catalyst. A catalyst is a chemical, any substance that lowers the activation energy required to get a reaction going. So in this case here, the activation energy was this red arrow that went from the reactant energy level all the way to the activated complex. Now, with a catalyst in place, what that does is it reduces the activation energy for a reaction. So instead of climbing a hill this tall of energy required, maybe it's around this tall. So it lowers the amount of energy required to climb a hill, and what's going to happen because of that is the reaction will go faster. You may have heard that catalysts cause reaction to speed up. Absolutely, it's because it's lowering the activation energy. Okay, so in the case of an exothermic reaction, we have the reactants at a higher level of potential energy. The products are at a lower potential energy level. All right, let's take a look at the endothermic reaction. And if you can imagine a mirror image of this exothermic, if you could take a mirror and folded over, we see almost a reverse image here, an endothermic reaction. Notice that the reactants in this case are lower in potential energy than the products are. So the products actually they finish being higher in potential energy than your reactants were, which means they're actually less stable than they were before. Well, what kind of chemicals would do that? Well, think of the chemicals that make up explosives or fireworks. Those chemicals initially are very stable. They don't do a whole lot of much at all on their own, and they're stored very safely. But you put those chemicals together that form fireworks or explosives, and all of a sudden your finished product has much more potential energy than it had before. This is much more unstable at this level than it did before. And you also notice the activation energy is much, much higher in the case of an endothermic reaction. It's going to take a lot of effort in order to mix those chemicals properly and do all the chemical procedures to them to turn them into fireworks or explosives. When they finish off, again, they'll be an unstable, higher potential energy product. Now, the delta H for this reaction is still going to be the difference between the products and the reactants, and it still has the symbol delta H there, which again stands for enthalpy, and this is the same thing. But what we're going to find out is that the enthalpies are different in terms of the signs that they have. Okay, so why are they different with their signs? Well, we'll get to that in 1 second. But what I want to do real quick is I want to give you a couple of vocab terms. So H is the letter that stands for enthalpy. It's the heat content of a system. And then delta H then will be the heat absorbed or released by a system. Okay, continuing on, if we go ahead and we dress up our delta H symbol a little bit better, we can now see delta H of subscript Rxn. Rxn just stands for reaction in chemistry. So what is the enthalpy change of a particular reaction? And you can see here it's the difference between the enthalpy of the products and the enthalpy of the reactants, the difference between them. So basically what that means is going to be products minus the H of the reactants. Okay, so if we take a look at our past slide from a minute ago, let's imagine that on this exothermic reaction graph, we'll say the products were at a level 5, we'll say the reactants were at a level 10. And these numbers are just arbitrary. But if we took our products and we subtracted the reactants from them, that would be 5 minus 10, which of course is negative 5. So it would be a negative value for an exothermic reaction. For an endothermic reaction, our reactants are at 5, our products are at 10, and if we go products minus reactant, of course 10 minus 5 is 5, and that's going to be a positive 5. So in endothermic reactions, we're going to find out that delta H is going to be positive. Okay? So exothermic reactions are always going to have a negative value. Endothermic reactions are always going to have a positive value. So if we had to apply that to this one here, which one would we choose? Would we expect delta H to be positive, or would we expect it to be negative? Okay, check it out for a second. Pause it if you need to figure it out. Okay, so let's say that my product level was 2 and my reactant level was 4. Okay, again, if I go products minus reactants, 2 minus 4, that equals, of course, negative 2. So in this case here, my delta H is negative, and this would qualify as an exothermic reaction. I also know it's exothermic because my products are at a lower energy level than my reactants are. Enthalpy of formation is the change that occurs when 1 mole of a compound is formed from its elements in their standard state at 25 degrees Celsius and 1 atm. So it's the energy required to form a particular substance. We have a special symbol for that one. It's delta H, and you have this little tiny naught symbol up here, and we have this little F down here as a subscript. The naught symbol signifies that it's in standard state. The F symbolizes formation, so that kind of gives away what this delta H is talking about. Formation, energy required in order to produce a particular substance. And that is also related to stability. And we could say this: the larger the negative value that the enthalpy of formation has, the more stable the new product is. So if we take a look at this example here, we have hydrogen gas and we have oxygen gas. And the two of these gases are pretty unstable the way that they are. Okay, we know that both of these are flammable gases, and they do much better in terms of stability when they bang into each other and wind up combining to form water vapor, H2O gas. It's a much more stable compound. And therefore, the delta H of formation of H2O gas from these two initial components is negative 483.6 kilojoules, which is very stable in comparison to each one of these products on their own. On the other side of that, we could say the larger the positive value, the less stable the new product is. So when we went up that big hill and our products were finished at a higher potential energy than our reactants, we saw positive values. Okay, this one here, C2H2, that's acetylene gas. We use that gas when combusted to weld metals together. So you know that one is very capable of high amounts of energy. This one here is called fulminated mercury, or mercury difulminate. And you can see this one even has a higher value of positive 270 kilojoules per mole. This one releases a lot of energy. And enthalpy of formation is also defined in terms of moles of product. It's these things we're making here. It's this acetylene, it's this fulminated mercury, it's this water vapor. Enthalpy change is the total change when 1 mole of substance is combusted. It's defined in terms of 1 mole of reactants. So we know if we are to combust something, we have to combust a particular substance, a reactant. And this has its own little fancy symbol. It's delta H with a subscripted C. And down here you can see what we call a bomb calorimeter. And this calorimeter allows you to combust different elements and substances in this little chamber. It's an oxygenated chamber. There's some ignition wires up here which are going to give you the spark needed to combust what's inside. And outside of the chamber is water, and this water can either go up in temp or go lower in temp, and it can be measured with a thermometer. It also has a stirrer here, so you can make the temperature change flow throughout your liquid sample and be more evenly distributed. Delta H can be calculated a number of ways. We're going to use Hasse's Law in order to do a lot of these calculations that are coming our way. Hasse's Law says the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for individual steps in a process. It's kind of complicated sounding. So I want you to think of, there's a destination that you need to get to. And no matter what pathway you take, and sometimes you can go on multiple different pathways, you're always going to wind up at that same place. That is what Hasse's Law is like. So in the translation down below it, it says if 2 or more equations are added, the delta H of the individual equations may also be added to find the delta H of the final equation. And how it breaks down is like this. This looks like a really scary formula, but don't let it scare you. It's not that bad. It basically says the sum of your product's enthalpy changes times however many moles there are. If you subtract the sum of the enthalpy changes of your reactants times how many moles there are, you'll get delta H of the reaction. And we'll be utilizing some version of this in a number of problems coming our way. We're going to take a look at an example, and we'll start very simple to begin. And what we're going to do is we're going to wind up adding 2 of these equations together to get us a final product. And when we add equations together, we're going to go ahead and handle cross-canceling like we did when we were working with net ionic equations, where if we see something on one side of the equation and on the other, we can cross-cancel it. We're also going to add delta H's together as we go through our problem so we can determine delta H for a specific reaction. So first, let's go ahead and add these 2 equations together and see what we get. So I see a 2H2 as a reactant on this side, and I see a 2H2 as a reactant on that side. That means you can cross-cancel it. I also see an O2 here, and I see 2 of them here. So I can get rid of the 2 and make there just be 1 left over. Then what I'm left with is 2H2O2, which is hydrogen peroxide, and that's a liquid. And I have my reaction arrow there, and my first product is 2H2O liquid, and we have 1 oxygen left as a gas. So that is the net equation when I add these two equations together. As far as the delta H is concerned, if I add these two together, I have negative 571 and I have positive 375.6. So what we're going to do is we're going to subtract one from the other. Since this is negative, what we'll do is we'll go ahead and subtract the first equation's delta H from the second one. If we do that, we get 0 here. We get 6 here. Got to borrow one more time. 16 minus 7 is 9. And 4 minus 3 is 1. So what I get is negative 196 kilojoules per mole. And that's really the pattern for doing a lot of problems where you're presented with a lot of equations and you have to put them together, combine them in order to reach a common destination. So let's take a look at another example. Carbon occurs in two distinct forms. It can be soft black material found in a pencil. Of course, pencils don't contain lead. It's actually graphite. Or it can be the hard, brilliant gem we know as diamond. Calculate delta H for the conversion of graphite to diamond for the following reaction. So here they give us a model equation to allow us to change these two equations here to finally wind up as this equation that we were given. Now, how do you do that? Well, you kind of own those equations that you see down below. You can do anything you want to them, including reversing them from one side to the other, or you can even go ahead and multiply them by something if you need a specific number of something. Okay? So let's go ahead and see how we're going to get carbon in the form of graphite into carbon in the form of diamond. And we're also going to calculate the energy change required for that to happen. So this first equation here, I have graphite as a reactant, and that's good because in the model equation, that's exactly what I see. However, in the second equation, I see diamond as a reactant, and that is not what I need. Instead, what I need is I need diamond as a product. So what I'm going to do is I'm going to flip the second equation around. So instead of having these two things as a reactant, I'm going to have CO2 gas as my new reactant. Then the arrow, I'm going to have C carbon in the form of diamond as my first product. And that's obviously a solid. And I'm going to have O2 as my second product, which is a gas. Now, when I flip an equation around, that also means I have to flip around the delta H. So negative 396 kilojoules becomes positive 396 kilojoules. Now, what I can do is I can get rid of the equation that I now have changed permanently here. And our last step is to see if there's anything that I can cancel out that's left over. And I see an O2 here, I see an O2 there, so those can go away. And what I'm left with then is I'm left with the exact equation that I see up above, and that's a good thing. So now I'm going to go ahead and I'm going to add these two delta H values together. Negative 394 plus 396, of course, is 2 kilojoules. And that is the enthalpy change from the conversion of graphite to diamond. Okay, and 2 kilojoules means that it will take energy in order to do that. So what if we wanted to find how diamond goes to graphite? Well, what's interesting is you'd have to flip the value of this, which would be negative 2 kilojoules, which means that this would be an exothermic spontaneous process, which means actually that diamonds, given enough time, will change into graphite. So when they say diamonds are forever, not quite exactly forever. Anyways, I hope this helped you understand how we work with these equations a little bit better. When you're given a number of equations, they give you a final point most of the time. In this case, it was this equation, and we had to work with the equations we were given by way of reversing them, by way of multiplying them by something in order for them to eventually look like the model one they gave us. And while we're working with those equations, we're also changing delta H's value, sometimes from negative to positive or positive to negative, and sometimes we're multiplying it by a given number. So I hope you understand energy, and I hope you understand enthalpy a little bit better. More to come. I'll see you next time.